Hey everyone, welcome to part 2 of our water pollution lecture series. This one will cover heavy metal, chemical, and oil pollution. Heavy metals are highly toxic. When we talk about heavy metals, we're talking about things like lead, arsenic, and mercury primarily, and they pose serious health threats to humans and other organisms. We're going to start off with lead. Lead is rarely found naturally in drinking water. There's a few places that it is, but most of the time when lead is in drinking water, it's because it's been put there usually accidentally by humans. It contaminates water when the water flows through lead-lined pipes or touches lead solder or brass fittings. A component of brass is actually lead, and this is actually commonly used in a lot of plumbing fittings. So as the water flows through there or sits there, you end up with lead contamination. Lead is a neurotoxin. It damages the brain, the nervous system, and the kidneys. Fetuses and infants are the most vulnerable to lead poisoning. Federal regulations over the past 30 years require lead-free pipes and fittings in all new buildings, but there's a lot of buildings that were built further back than 30 years ago, so lead contamination remains a problem in older buildings. I mean, my house is older than 30 years old, so I know that a lot of the pipes that lead into it probably have lead solder, and so there's probably the potential for that in my water supply, as is there probably in yours. And this is lead contamination in water has been in the news. If you have been following the Flint water crisis, let me just give you a quick rundown on that. So Flint decided that they weren't going to buy municipal water and they were going to get their own water out of a local river, the Flint River. Well, the Flint River is pretty polluted and it's got a low pH. So Flint is an old city and a lot of the pipes in the city are made of lead or have lead solder. So when they began running, the water's been treated, but the water's pH is lower than the other municipal water supply. So, and they were doing this to save money. So when the low pH water began flowing through the lead pipes in Flint, it actually leached some of that lead out into the water, dissolved that in higher concentrations, and so the water had high concentrations of lead, which of course was unsafe. So many people were exposed to high concentrations of lead in the Flint water. And this is still going on, actually. It hasn't been resolved. So in contrast to lead, arsenic occurs naturally in the Earth's crust. Well, lead does too, but lead is not often found naturally in drinking water. Arsenic, however, is. It dissolves into groundwater and can lead to drinking water contamination. Human activities such as deep mining for water wells where the rock is cracked, or the use of arsenic as a wood preservative can lead to arsenic pollution in groundwater as well. So let me just talk a little bit about that arsenic and wood preservative. Wood, when it's placed in the ground, rots, right? So in order to preserve it, they dip it in arsenic, which leads to the arsenic kind of getting into the soil, and then once it's in the soil, it gets into the groundwater. One of the most egregious uses of arsenic treated wood is in playgrounds. Wooden playgrounds are frequently made with lumber that's been treated with arsenic, which I think is fairly ironic. Arsenic contamination has been associated with cancer of the skin, lungs, kidney, and bladder. Even small amounts of arsenic in drinking water can cause serious health effects. Arsenic, however, is not a quick killer. It does take some time, about 10 years of exposure to small amounts of arsenic to see a deleterious effect like cancer. Naturally occurring arsenic contamination is a problem across the world, and in the United States, the problem is most acute in the Midwest and the Western states. And you can actually see that here on the map. Any part that's yellow or red is going to have a greater propensity to have arsenic in the groundwater. And that is just because the underlying parent material, the rock there, is naturally arsenic containing. So the soils are naturally arsenic containing, if you remember how soils work. Arsenic can be removed with fine membrane filtration, distillation, and reverse osmosis. So if there is a problem with arsenic in the groundwater, it can be removed, but you have to be kind of diligent about it. Mercury. Mercury occurs naturally, again, in the ground and in the crust, but most mercury pollution that we see in groundwater is the result of human activities. 2/3 of anthropogenic mercury comes from the burning of fossil fuels, particularly coal. So where does mercury come from? Usually from coal. And what happens is as we burn coal, the mercury particulates go up in the air, they blow across, and so downwind of coal-fired power plants, you often have pretty severe mercury contamination in the soil and the groundwater. Other sources of mercury include the incineration of garbage, burning garbage, hazardous waste, medical and dental supplies, and the production of cement. Believe it or not, when you produce cement, the production of cement actually has several negative environmental consequences, but one of that is that there is off-gassing of mercury. Petroleum drilling is a source of both mercury and lead pollution. So if contaminated wastewater or drilling mud is disposed on site, as it sometimes is, it can pollute soil and groundwater with mercury and, of course, with the lead, but now we're talking about mercury. So who emits the most? China emits the most mercury because China burns so much coal. Since they're burning, they have tons of coal-fired power plants. Coal emits mercury, so they've got a lot of mercury pollution. That's the most mercury from a single country. Asia, as an area, produces half of the world's mercury emissions. Inorganic mercury, just like periodic table Hg. Inorganic mercury is converted into methyl mercury by anaerobic bacteria. And methyl mercury is the real bad guy here. Methyl mercury is highly neurotoxic, particularly in young children and developing fetuses. So whereas inorganic mercury, it's not absorbed well by the body. Some of it is, but not so much of it. Methyl mercury, on the other hand, is very readily absorbed by the body. So it's very dangerous. Methyl mercury also biomagnifies. So species at the top of a food chain have higher concentrations of it in their bodies. So your book talks about in 2008, tuna sushi from around New York City was tested for mercury and found to be contaminated. And this was in many locations around the city. Just 6 pieces of sushi a week exceeded the EPA standard for human consumption of mercury, which most people are eating way more than 6 pieces of sushi if they're eating it, especially even at one time. So tuna is a top predator, and because methyl mercury biomagnifies, the tuna is going to have a pretty high concentration. And then, of course, you're eating more than 6 pieces, so you're getting a fair amount of mercury. One of the things, you guys know that I'm from the Detroit area, and my family all lived around the Great Lakes. There's a lot of advisories. If you fish in the Great Lakes, the mercury contamination there is a problem, and you're advised to eat no more than 1 serving of fish that was caught in the Great Lakes per week, because of the mercury contamination there, especially if you're of childbearing age. And there's signs warning you about that. If you're a woman of childbearing age, they say really no more than 1 serving of Great Lakes fish a week because of the risk of mercury poisoning, which is kind of scary when you think about that. So I have posted the video of the SciShow YouTube about Minamata disease. So Minamata disease happened in Minamata, Japan. The effects began to be seen in the 1950s. And by 1959, they had figured out what was going on there. The video will give you more information there, but basically it was illegal dumping of industrial waste into Minamata Bay. And people and animals in the area were experiencing methyl mercury poisoning. It was pretty intense. Acidic deposition occurs when acids are deposited on the earth as rain, snow, hail, sleet, fog, which we call wet acid deposition, or as gases or particles, which we call dry acid deposition. These acids attach to the surfaces of plants, soil, and water. Because this is our water pollution unit, I'm not going to talk about all of the effects of acidic deposition. There's soil effects, there's negative effects on photosynthetic organisms, but this is water pollution. So we're going to talk primarily about what happens when acidic deposition gets into groundwater or surface water. So acidic deposition is most commonly associated with the burning of coal, again, which releases sulfur dioxides and nitrogen dioxide, which combines with water vapor in the atmosphere to create sulfuric and nitric acid, respectively. So it's really the burning of coal is releasing these pollutants. They're mixing with water vapor and they're creating acidic precipitation. Acidic deposition in water lowers the pH of the water. And obviously, things that are living in water are adapted to certain pH range, and usually they want the pH to be pretty tight within that range. They don't do well even with a small change in pH. So acidic rainwater leaches aluminum ions from soil. Once the acidic precipitation runs down into the soil, the aluminum ions are freed, and those aluminum ions flow into lakes and streams. Aluminum is a heavy metal. We've talked about it, and it has bad effects on aquatic life. It actually coats the gills of aquatic life, and they suffocate. So some aquatic species are more acid and aluminum tolerant than others, but all species are harmed in some way when the pH is lowered from normal values. So I just gave you a little snippet here on the side. These are some critical pH levels for aquatic organisms. Snails, clams, bass, crawfish, mayfly, whatever. They're over here on the side. This is where they like that if it goes below this critical level, then they cannot live. And I mean, I'm surprised actually frogs can tolerate a pH of 4. I know that amphibians are pretty sensitive to pH changes, so I'm surprised that they can even live at a pH of 4. But if we get a significant pH change, you're going to end up with water that is devoid of life. And there are lakes that where there's no aquatic life because the pH is so low because of acidic deposition or because of the leaching of aluminum ions. And they kind of go hand in hand. Acidic precipitation falling on a surface body of water is going to lower the pH outright, but then you also have the acidic precipitation falling on the land, which leaches the aluminum ions, which run off into the surface body, which suffocate the aquatic life there. So it's kind of a double whammy. So water pollution can also occur due to acidic mine drainage from abandoned mining sites. And again, we've talked about this just a little bit. So what's the mechanism here? Well, you have mines, and when they become abandoned, they often flood with groundwater or rainwater seeps in there and floods them. The water and the air allow iron pyrite, which is a type of rock, to break down and produce hydrogen ions, which lowers the pH of the water. And the acidic water then seeps up onto the surface into streams, or it gets into the springs that feed the surface water. The low pH mine drainage causes the leaching of zinc, copper, aluminum, and manganese from soil into the groundwater. So we have even though in addition to the low pH mine drainage, which causes its own problems for aquatic life, like we just talked about, we also have additional leaching of other metal ions, like we do with acidic deposition, wet deposition. So we got the leaching of zinc, copper, aluminum, and manganese, and all of these, when they're leached out of rock, cause problems for aquatic life as well. So the biggest issue with acidic mine drainage, besides the environmental effects, is cleanup is costly. It's often very difficult to do. There's been a couple of different strategies proposed. You could divert the stream into a limestone bed to raise the pH, and that's pretty much the only one that people do in any large scale. But it's really, really difficult to clean up. And most of the time, these mining companies that have abandoned the mines are no longer even in business. They're defunct. So the cleanup, the actual physical cleanup and the cost of cleanup then falls to state and local governments. And this is not an easy solution, and it is also not cost effective. So it's a pretty big burden. So another thing that gets into water, synthetic pesticides, and the use of synthetic pesticides often have unintended consequences for marine or freshwater species. So pesticides that are designed to kill one species or a certain range of species can be harmful or lethal to a completely unrelated species. And this is what we are talking about unintended consequences. Endosulfan, which is an insecticide, has been shown to be lethal to amphibians, even in very small quantities. So the company develops an insecticide. It's great, to kill insects, but then it gets into the water when it's sprayed, and we have amphibian deaths. Amphibians are really, really sensitive to chemicals in water. Well, why? Because they breathe through their skin, partially. They have lungs, but they also breathe through their skin. So they have gas exchange, and their skin is super sensitive. It's an organ of respiration. So imagine putting a chemical into your lungs like that. That's basically what you're doing to an amphibian when you put chemicals in the water. And obviously they don't tolerate that well. We have lots of pesticides cause unintended amphibian deaths, especially, when they get into the water. So we've talked about DDT before. DDT is a pesticide that was designed to kill mosquitoes, and it's really good at that. The problem is it also has unintended consequences. It biomagnifies up the aquatic food chain. When it gets into water, it gets into the plants, and then it gets into the things that eat plants, and then it gets into the little fish, and then it gets into the big fish, and then it gets into aquatic birds. And it causes reproductive harm in fish-eating birds by thinning the shells of their eggs. So when the eggs are abnormally thin, when the bird sits on the egg to incubate them, the egg breaks and the baby dies. So again, DDT was designed to kill mosquitoes, and it's good at that. But it also, it's persistent. It's a persistent organic pollutant. It hangs around for a long time. And it also causes unintended reproductive harm to fish-eating birds. Recently in the news, the weed killer Roundup, which we talked about Roundup and Monsanto before when we saw Food Inc. So the weed killer Roundup has these inert ingredients, and all weed killers do. If you go to Home Depot and you look at a pesticide or a weed killer, it'll list the active ingredients, and then it'll say like 99.2% inert ingredients, but it doesn't list what those are. The reason that they don't have to list what they are is because inert ingredients are considered trade secrets. Now, when we hear the word inert, we tend to think like inert gases where they don't react with anything. But in the case of, pesticides or chemicals, inert doesn't necessarily mean non-harmful. It just means that that's not what the product was designed to deliver. So, it could just be water, but it's usually a combination of chemicals. So there's an inert ingredient in the weed killer Roundup that is super toxic to amphibians. Again, kind of like endosulfan. Again, inert ingredients are considered trade secrets. Companies do not have to legally disclose what chemicals they contain. So this is problematic. And it's really difficult to trace it back. This took a lot of kind of environmental science detective work to figure out what was going on here. Pharmaceuticals and hormones. They also pollute water when treated wastewater is dumped back into bodies of surface water. And I want you to think back to the first video that we watched. Once wastewater is treated and then disinfected, it is dumped back into bodies of water. Well, one of the things that traditional sewage treatment plants cannot filter out is pharmaceuticals and hormones. And they get in there from human excrement because we take them into our bodies and then we excrete the metabolites of those into the water. They're also present in the excrement of livestock because livestock are fed antibiotics, hormones, steroids, and all kinds of things to manage infection and to control their growth. And again, if you remember from the wastewater presentation, livestock manure can overflow from manure lagoons during heavy rains and can pollute local waterways. So we end up with pharmaceuticals and hormones in bodies of water. The level of threat to human health from drugs and hormones in water is currently unclear. You can imagine it's probably not great, but we can't really point a finger at this is happening in humans because of pharmaceuticals and hormones in the water yet. But we can point a finger with hormone pollution in particular because it's been shown to cause reproductive harm in fish and amphibians. I told you guys, make sure to read the Chesapeake Bay case study at the beginning of your chapter because in the Chesapeake, estrogen compounds from birth control pills in treated sewage water that was discharged into the bay have caused 23% of male largemouth bass and 82% of male smallmouth bass to develop into hermaphrodites. Hermaphrodites are organisms that have the characteristics of both sexes, so both male and female. So they're technically male on the outside, but inside they're growing eggs instead of sperm. Obviously, that's a problem, and it leads to infertility. Well, if the males have eggs instead of sperm, then they cannot fertilize the female eggs, and we get a loss of species, loss of biodiversity there, and a reduction in the species number. So clearly that's a problem, and it is caused by birth control metabolites in discharged wastewater. I found this and I kind of liked it. I think it describes a little bit better what's going on in terms of how pharmaceuticals and other hormones get into the water supply. So if you look here, I mean, I'm going to just say it's a little biased because it's like, talking about the production and how prescription drugs are profitable, and they are. So, I mean, I don't want to say that they're not profitable, but it starts here with the production of pharmaceuticals and the distribution of pharmaceuticals to humans. Those things are normal things that we talk about, right? We get drugs are produced, drugs are distributed to humans. So I don't know if you've ever heard this, but back when I was younger, people said flush your drugs down the toilet when they're expired or when you no longer want to do that. When you no longer want to use them. Well, that's a really, really bad strategy. Do not flush your drugs down the toilet. It gets into the water supply. You cannot get them out. Now, most pharmaceutical companies have mail back programs where you can mail them back with a postage paid envelope, mail them back the unused drugs, and they will dispose of it properly. Do not also put them in the garbage. If you put them in the garbage can, they can either be used illegally by others or they can enter local waterways through a municipal dump. If you are using them and you're taking them, you're excreting metabolites of those drugs into the toilet every time you take a poop or go to the bathroom. So taking pharmaceuticals, taking birth control pills, that stuff comes out in your excrement. And once it goes down the toilet, it goes to a sewage treatment plant. So as you know, sewage treatment plants, they can't filter those chemicals out. There's no way for that to happen. The only stage that could theoretically filter that out would be tertiary, and it's just not, tertiary is optional and it's just not done. So the treated sludge can be used as fertilizer. If the sludge is used on agricultural crops and it contains hormones and steroids and pharmaceuticals, then when it is put on the crops as fertilizer, when it rains, it's also returned to water bodies. We have, again, the lovely manure lagoon overflow during heavy rains. Livestock and poultry are treated with high levels of pharmaceuticals and hormones to keep them healthy in CAFO conditions. And then we end up with a problem here. So they're talking here about filtration. Water is filtered to drinking quality, but residual pharmaceuticals remain. So after the treatment, the sewage treatment, we can't really get the pharmaceuticals, the hormones, the steroids out. So here we are with drinking water. It can be, you put it back into bodies of water, surface bodies of water. And when we pump the water out of those bodies of water in order to treat it for municipal use, it still has chemicals in it. So the chemicals end up back in the drinking water. This number right here, 80%. There was a landmark study, and I actually went ahead and read that a couple of days ago so that I could make sure that I understood what was going on. 80% of 139 streams that were sampled across the United States in 1999 and 2000 contained at least one pharmaceutical drug. 80%. That's a lot. That's a lot of drugs. And some of them contained way more than that. So obviously, the closer you are to a heavily inhabited area, there's going to be more drugs in the water. But yeah, it's a problem. Military and industrial compounds can also pollute ground and surface water. Perchlorates are used in rocket fuel. And that doesn't, you're like, rocket fuel contaminating my groundwater. But believe it or not, there are places that are heavily contaminated with perchlorates. Anywhere that's close to a place that makes rocket fuel or tests rockets is going to have perchlorate contamination. Drinking water contaminated with perchlorates disrupts the proper functioning of the thyroid gland. So you can have hypothyroidism or hyperthyroidism, which causes all kinds of health effects, including, growth disruption. PCBs, polychlorinated biphenyls. These are bad. They are no longer used in the United States. Their manufacture was banned in 1977, but they were used to manufacture plastics and to insulate electrical transformers. So plastics that were created before 1977, PCBs are in them. And PCBs are persistent. They hang around for many, many years in silt and in sediment in rivers today. Ingestion of PCBs is carcinogenic. It causes cancer. There's a case study in your book talking about whether or not with PCB cleanup in a river, sometimes it's best just to leave the very contaminated river sediments stay where they are, because when you dredge the river, when you suck all those sediments out with a big backhoe, you actually create higher levels of PCB contamination before it settles all back down again. They just hang around for a super long amount of time. But they get into waterways and they cause all kind of problems. So PBDEs, this is something that we've just recently kind of figured out is causing problems. PBDEs are polybrominated diphenyl esters. Well, what are they? They are flame retardants that are sprayed on a variety of materials, especially fabrics. Your pillow contains PBDEs. A lot of children's nightwear, the jammies that children wear that say that they're flame resistant, they're sprayed with polybrominated diphenyl esters. Unfortunately, PBDEs are shown to cause neurological damage, brain damage, especially in children. So if your children are wearing flame retardant jammies, they're getting high doses all night long of PBDEs in their system. PBDEs are also, they negatively affect fish and aquatic birds. They've even been found in human breast milk. Obviously, if it's bad for developing children, it's really bad for PBDEs to be in breast milk, but you absorb them by sitting on textiles that are treated, sitting on or wearing textiles that are treated with this flame retardant material. Brain damage is the neurologic damage is the main problem with PBDEs. And they also hang around for a long period of time. They don't break down well. This is a picture that was also in your book. This is a picture from 1952 of the Cuyahoga River in Ohio. This river actually caught fire, not just once, but several times. 52 was the first. It caught fire again in 69. The Cuyahoga River runs through an industrial area of Ohio, and the industrial plants were dumping chemical toxins into the water. There was industrial pollutants floating on the surface of the water, and a stray spark actually ignited the river, and it caught on fire. The surface of the water was burning. So you can see that the firefighters here on the dock right there are spraying the river to try to put it out. And then this tugboat is also a firefighting tugboat here. But the Cuyahoga was once considered one of those most polluted waterways in America. I mean, we're talking bad industrial pollution, but it's much cleaner now. And the reason it's much cleaner now is thanks to legislation. The law changed and said you cannot put crap into the water. It limited industrial dumping, and the Cuyahoga, due to the legislation and to the cleanup efforts of river activists, is much, much cleaner, and aquatic life has returned. So, when we talk about the good old days, I always like to remind people, the air and the water used to be so much more polluted. Even when I was growing up in the 70s, it's hard for me to explain to people and explain to you guys how dirty things were. And it was the result of the 1970s Clean Air Act, Clean Water Act, that have allowed these once really polluted areas to recover. Do we have a ways to go? We sure do, but it's way better than it was. And it's the result of government legislation. So don't let anybody tell you it doesn't work. It does. Oil pollution in water comes from many different sources. The three biggies are tanker accidents resulting in oil spills, offshore drilling accidents, and natural oil seeps. So the most famous tanker spill, and one that you need to know about for the exam, occurred in 1989, and that was the Exxon Valdez, and it ran aground in Prince William Sound, Alaska, which is a very environmentally sensitive area. Lots of bird life, lots of marine life there. It spilled lots and lots of oil, millions of barrels of oil spilled there. Many species were harmed initially, and there's a huge cleanup effort. People were washing birds with dish soap and getting all their feathers cleaned, and there was lots of marine death and bird death surrounding this. A lot of shoreline cleanup. 20 years later, environmental groups went back to kind of look at species distribution, see long-term what has happened. So many species that were severely harmed initially have rebounded. A lot of the seabirds and shorebirds, you couldn't tell the numbers looked pretty much normal from before the spill. But there were several key species that have not rebounded, particularly mammalian species. Killer whales and sea otters, their numbers are still very, very low in the area. And there's all kinds of theories as to why that is, but they're both, killer whales and sea otters are both predators. So when we're talking about getting concentrations of toxins up the food chain, there's some thought that they're getting damage to organs, particularly their livers, by eating organisms that were contaminated with toxins from the oil further down the food chain. So those top level predators have still not recovered. The other thing is that they estimate when they dig some test pits on the beach, even though the beach looks clean, when you dig down just a little bit, you find oil. So they're thinking about 15,000 gallons of oil still pollute the coastline. It's still there, and it's probably going to take hundreds of years to break down. The most famous offshore oil spill occurred in 2010, and again, this is one that you need to know for the exam. This was the explosion and the sinking of the British Petroleum, the BP Deepwater Horizon drilling platform in the Gulf of Mexico. It was obviously all over the news because it was a humongous environmental disaster, one of the worst in history. The spill contaminated beaches, wildlife, estuaries. It polluted a huge amount of surface water. The magnitude of the spill was 20 times greater than the Exxon Valdez. We thought that one was big. BP dwarfed them all. The main problem with the BP Deepwater Horizon platform is that they couldn't plug the underwater oil plume for many, many months. It just kept spewing oil from the bottom of the ocean up to the surface before they got a handle on how to actually plug that oil well that was just basically spewing millions of barrels of oil a day into the Gulf. The biggest surprise, I think, for most people is that the largest source of oil pollution in the ocean is actually from natural oil seeps. And I'm just going to say this particular image here came from an oil and gas exploration site. However, it's the same image that's in your book. I did verify the numbers because I was surprised by this. Oil pollution in the ocean is 62% of that in North American waters. Now, it's a little bit different in other waters, but in North American waters, 60% of the oil that's floating around in the ocean is coming naturally from the ocean floor. This is one of the reasons we do offshore drilling. There's a lot of oil under the ocean floor. When we talk about oil cleanup, right, we have to consider that some of this is not clean upable because it's coming naturally from the ocean floor. So we have to assess both natural and anthropogenic sources of oil pollution when we talk about cleanup efforts. So how can we get spilled oil cleaned up? Well, it's kind of difficult. It depends on where it's coming from. So I talked about Deepwater Horizon and underwater wells. When underwater wells are releasing huge plumes of oil, when there's been a disaster like BP, it's incredibly difficult to plug them. They have ways to do it, but it's deep in the ocean. It's dangerous. It costs a lot of money. There's no really good consensus about what the best way to cap a rogue underwater well is. It's really highly dependent on how deep it is and how it broke in the first place. So I didn't actually include that here because there's not an agreed upon way to cap that and clean it up. Now, the oil at the bottom eventually reaches the top of the ocean. So we're going to talk about oil spill remediation primarily from a surface perspective. So for surface spills, the slick can be contained with booms, and the booms are these floating, they're floating walls basically, and they extend several feet down from the surface. So they float on the surface, and they've got these little walls that extend further down on the surface. Once the slick is contained with a boom, the excess oil that's then, in a contained area can be sucked off the surface with vacuum hoses. They send a ship out with it, like it's a big vacuum ship, and it sucks the oil off the surface. In shallower waters, the booms are often absorbent, and they both contain the oil and they absorb the oil. So they don't send the ship out with the vacuum hose. That's for deeper water spills. They'll absorb the oil with these booms, and there's some kind of absorbent material in there. It can be natural or it can be man-made. Another approach to surface spills is the use of chemical dispersants to break up the oil before it reaches coastlines, because the big deal is you don't want the oil washing ashore. Once it does that, we've got all kinds of additional problems. Chemical dispersants are effective. They're basically like detergent. Y'all know what detergent does to oil for your dishes, right? It breaks it up and washes it away. But dispersants are toxic to marine life. So they're effective, but they're not great to use, and they're usually used pretty sparingly. A third approach to cleaning surface oil spills is to use genetically engineered bacteria to eat up the oil. This is called bioremediation, and this technology is still in its infancy. They're still trying to figure out the best way and the best type of bacteria to engineer to do this. But I'm going to tell you what, this is a huge area of research right now, and very, very profitable. Lots of people trying to find ways to bioremediate oil spills. Once spilled oil does get ashore, like if your cleanup efforts offshore are not effective and it spills ashore, or if the spill is close enough to shore that it gets there immediately, it can be washed off using high pressure hot water hoses or manually scooped up and disposed of. Now, the high pressure hot water hoses might sound attractive, and that's what they did in Prince William Sound to clean the beach of oil there. The problem is, what they found out later is that when they spray this hot water to get rid of the oil from the beach, they're actually also spraying off all the little marine creatures from the beach that live there. So they're like basically scouring the beach, and they are taking off the first layer of sand on the beach, which is problematic because that sand there is part of the nutrient cycle of the beach. So they're basically taking away the top layer of life and the top layer of sand, which is part of the decomposition cycle on the beach. So when you use it, it actually takes longer for the beach to recover. Letting the natural action of the waves and tides clean the coast takes a longer amount of time. And when they look back at the hot water versus this natural action, more oil tends to remain in the cracks and crevices, especially of rocky coastlines, when you don't hit it with the hot water. But in the long run, like overall, when you're looking at the big picture 30, 40 years down the line, letting the natural action of waves and tides clean the coastline may be less harmful overall. On the beaches where they sprayed the hot water, they looked clean, right? They looked a lot better than the beaches where they didn't. But the biodiversity hasn't returned there as quickly. So maybe letting nature take its course is a better action there, although it doesn't feel better at the time. You see what I'm saying? All right, that's the end of this one. Thanks, guys.